Today we're going to finish up our discussion of chemistry of seawater, particularly by tying off some loose ends with dissolved gases and then talking about pH of seawater a little bit, which kind of follows from that. And then hopefully, I'm not sure if I'll get a chance to get to this today, but we'll start talking about winds and atmospheric circulation, which turns out to play an important role in causing the ocean to circulate, causing surface currents in the ocean, which is obviously important for oceanography. And so you can think of the goal of the next couple of days. I'll be happy if, among other things, you have some sense of why it might happen that you can have a column of air that has fire on the bottom, as was the case in the forest fire we had up in the San Gabriel Mountains earlier in the summer, but water at the top, okay, from the same phenomenon. All right, so at the end of the day on Wednesday, or actually for most of the day on Wednesday, we were talking about things like how salinity and temperature affect the density of seawater and what implications that has for the structure of the ocean. It's layering by density, it's stratification by density. Basic point being that warm freshwater in the ocean tends to be the least dense, and cold salty water tends to be the most dense. And of course, dense things tend to fall to the bottom. So in the ocean, the bottom water is usually very cold, in particular less than about 5 degrees Celsius, in some cases below 0, and somewhat salty at least. So that if we go to a typical spot in the ocean, in this case we're in the South Atlantic, but we could construct superficially similar plots in many other parts of the ocean. Okay, everywhere in the ocean pretty much density increases with depth, from a surface layer that's mixed up by waves and by wind blowing across the ocean's surface and churning things up, and a transition to a relatively homogeneous, cold, dense, deep water. That transition from the surface mixed layer to the deep water in the ocean, by which I mean water that's usually below about a kilometer or two, is called the picnic line. It's the region in which the density of seawater changes. In this particular location, the change in the density of seawater is dominated by a drop in temperature as you get down below 50 meters or so, down to about 1,000 meters, at which point the temperature of that ocean water is only about 2 degrees Celsius. Salinity can also affect the density of seawater. In this case, it's doing something kind of weird and complicated. It's actually salty at the surface, becomes a little bit fresher, and then gets saltier again as you go deeper. In this case, the change in temperature, getting colder, is what's controlling the density for the most part. It's getting denser even though it's getting fresher with depth in the top 500 meters or so. But in particular, the deep water in the ocean is, the first order, kind of boring. It's all cold, okay, not very much difference in density from one part of the ocean to another, fairly uniform salinity as well. All right, so are there any questions about that before we move on? Okay, we also started talking about dissolved gases in the seawater. The two most abundant gases in the atmosphere, nitrogen and oxygen, they really dominate our atmosphere. Like 99% of the atmosphere, at least in the absence of water vapor, is nitrogen and oxygen. And they're pretty important in terms of being dissolved gases in the ocean. Nitrogen in particular, yeah, it's pretty common as a dissolved gas, but it actually doesn't do very much in the ocean. Very few organisms can use N2 as a nutrient, and they usually don't occur in sufficient abundance to actually change the abundance of nitrogen in seawater to any significant extent by taking it up or generating it. And therefore, it's more or less conservative. It behaves in seawater somewhat like sodium and chloride do, fairly consistent composition from place to place. Its solubility depends on temperature, so depending on the temperature of seawater, it may change somewhat. But by and large, it's a fairly boring story. Oxygen and carbon dioxide are more interesting because they're consumed and produced by different types of biological activity in the oceans. And carbon dioxide is also very interesting because it is much more common as a dissolved gas in seawater than it is as a free gas in our atmosphere. CO2, for some reason, is really soluble compared to the other gases in the atmosphere. So just to show you that oxygen is not conservative in seawater, it does not obey the law of constant proportions. It's being produced and destroyed somehow. We can look at another one of these depth sections in seawater, and this is near Hawaii. But you could make a similar plot pretty much anywhere you wanted to go as long as you weren't right up at the poles. And what's shown here is two things. So the yellow is temperature and the blue is oxygen. Temperature does what it usually does near the tropics. Fairly warm in the surface layers, actually very nice, 25 degrees Celsius, perfect swimming water. But when you get down below a few hundred meters, it's getting really, really cold, down below 5 degrees Celsius again, like it is pretty much everywhere in the ocean. Oxygen is doing this interesting thing where in the top, a couple hundred meters, it's not very interesting. There's not very much happening with it. And once you get below that, the abundance of oxygen falls off very sharply. And for most of the ocean is much less abundant than it was near the surface. Okay, so this is telling us that once you get below a few hundred meters in the ocean, oxygen seems to be getting consumed. It's being lost. So much of what we're going to talk about today is what that process is and why it happens where it does. And we'll come back to this when we start talking about biology in more detail after the second midterm. Let's focus on carbon dioxide for a minute, though, to sort of finish off this topic of chemistry of seawater. So remember, CO2, it's very rare in the atmosphere compared to nitrogen and oxygen. It's about 0.04% or something like that of the atmosphere. It's enough to cause issues for climate change and stuff like that, but in terms of its volumetric abundance, it's actually pretty rare. It dissolves from the atmosphere into the ocean, but for some reason it's much more soluble. And the reason I'm about to get to actually is quite interesting. It's also worth pointing out, by the way, that it can also be produced in the ocean by much the same process. It turns out that oxygen was getting lost from the ocean. So once you get below a few hundred meters in the ocean, typically CO2 abundances start to pop up at the same time that oxygen abundances are starting to decrease. CO2 is actually consumed by photosynthetic organisms like plants. And the really interesting thing, and the reason why it's so common in seawater, is that it actually undergoes a chemical reaction with water, which is different fundamentally from the way that oxygen and nitrogen interact with water. They pretty much dissolve. You have an O2 molecule, two oxygen atoms stuck together by a covalent bond, and it goes through the water-air interface, and it's bouncing around inside liquid water, still in the form of O2. Same for nitrogen. You have two nitrogen molecules bound by a very strong covalent bond. It can go past the air-water interface, and it's bouncing around inside, knocking off of water molecules, maybe interacting a little bit with oxygen, hydrogen bonding capabilities, but not really to any significant extent. Just bouncing around, and it's pretty much the same form it was in the atmosphere. It just happens to be in the water. CO2, when it gets into that water, actually reacts with it, and its fundamental structure changes. So the chemical reaction is that a carbon dioxide molecule reacts with a water molecule to make this complex thing that has a water molecule and a CO2 stuck together to make a carbonate, carbonic acid in this case, where the carbon, instead of just being bonded to two oxygens, is actually forming covalent bonds with three oxygens. Okay, so it actually makes a little triangle with a carbon in the center and three oxygens arranged around it. And attached to those oxygens are a couple hydrogens in the case of carbonic acid, but it's an acid. Definition of an acid being something, at least for the purposes of this class, being something that can give off hydrogen cations when it's in solution. And in fact, that's pretty much what it does. This stuff is quite rare in seawater, tends to give off a hydrogen, become bicarbonate, which is an anion. It's negatively charged. And it can even go further, lose another hydrogen, and become a carbonate ion, which has two negative charges. This hopefully looks fairly familiar to you when we were talking about carbonaceous oozes, calcium carbonate skeletons, the calcium carbonate condensation depth. We were talking about shells made out of calcium carbonate, which is CaCO3. Okay, so this is the same stuff that goes to make those kinds of shells. In this case, it's dissolved, however. So given the composition of seawater with its salinity and its temperature and the abundance of CO2, this is pretty much how that reaction goes. Okay? CO2 dissolves in seawater, and some of it stays as CO2, but it's a tiny, tiny bit. The vast majority of CO2 that dissolves in seawater actually reacts with that seawater to make bicarbonate, okay? In which process it's giving off an H+. So it's acting as a little bit of an acid, and a little bit of it actually goes far enough to make carbonate. But the vast majority of CO2 that's dissolved in seawater is no longer in the form of CO2. It's in the form of bicarbonate. And that turns out to be really important for understanding how ocean water can act as an acid or base. Its abundance, of course, varies in the ocean. It gets consumed in the parts of the ocean where photosynthesis is happening. I'll come back to this. And it gets produced in parts of the ocean where decomposition of organic material is occurring. And all of those things can change not just the overall abundance of CO2, but actually, to some extent, this balance between bicarbonate and carbonate and CO2. Okay, let's look at that in a little bit more detail, those processes that affect the abundance of CO2. Okay, photosynthesis, this is probably review for most of you, but just to get everybody on the same page. The idea here is that plants on land and phytoplankton, which are organisms drifting in the ocean that serve much the same function that plants on land do, can actually harvest energy from sunlight and use the chemical building blocks in their environment to create organic material. Okay? So they make things like sugars, which is stored chemical energy, and they make it from water, from carbon dioxide, using sunlight energy. Okay? So this is a formation, it's a transformation of sunlight energy into chemical energy that they can then carry around with them and use whenever they want it. A byproduct of this reaction is that oxygen is actually formed. In the process of consuming CO2 and water and making sugars, there's extra oxygen left over at the end, which to some extent gets released into the environment. And of course, because this is a process that is converting light energy into chemical energy, you got to have light. And so photosynthesis is confined to the parts of the ocean that are light enough, okay, the top 100 meters or so, depending on where you are. So in a simple little box diagram, we could say, okay, we have some seaweed here, and it's certainly getting light, and there's plenty of water because it's, sitting in the ocean. In this case, we're right at the surface, so there's CO2 coming in from the atmosphere, there's CO2 dissolved in the water, and as long as that is all working fine and there's photosynthesis, the system is going to be spitting out oxygen and stored chemical energy. And we can actually write out a crude chemical reaction for this process where what we're putting into the reaction is water. In the case of plants in the ocean, they're sitting in seawater, which is like 97% water, so that's usually not a limiting quantity. It's consuming carbon dioxide, which is fairly common as a dissolved constituent in seawater, but varies from place to place. And of course, it requires sunlight, which is generally only present at the top of the ocean. So this is only going to happen near the top of the ocean. And the byproducts of that reaction are stored chemical energy in the form of sugars and oxygen. Okay, so this is a process where CO2 is lost and oxygen is created. So you can think of photosynthesis grossly as a chemical process being left to right in this picture. In order for it to work, you need all the things that are present on the left, and as long as it's working, you'll be creating all the things on the right. Respiration, which is what we do, what we usually think of animals as doing, is kind of just the backwards form of the same process. We consume chemical energy, food, and we breathe in air and remove some of the oxygen from that air and combine those two things, breathing out carbon dioxide and generating water as well. Okay, we don't generate sunlight, so it's not strictly backwards. Instead, we use that energy to make our lives work. Okay, so we're not light bulbs. However, we're using that chemical energy to run around and find things to eat, fight each other, so on and so forth, whatever needs to be done. So respiring organisms, the animals, and in the case of the ocean, things we call zooplankton, essentially gather sugars, gather stored chemical energy from their environment, and they burn it using oxygen to release the energy for their own purposes. Okay? Creating water and carbon dioxide. And of course, as long as we have those things available, as long as there's oxygen dissolved in the seawater, and as long as there's organic material that can be had, this process can occur. And it actually tends to occur, to some extent, all the way through the water column and even into the sediment to a certain extent. photosynthesis can only happen where sunlight is. Respiration can happen wherever there's organic material. Okay, so the story of why oxygen varies the way it does hopefully makes a bit more sense now. Okay. Photosynthesis can only happen up on the top of the ocean, and that's the process that generates oxygen. Respiration can happen anywhere in the ocean, presumably driven by organic material that's falling down from the photosynthetic zone. Okay? And that process is consuming oxygen. And once you're this deep in the ocean, you're not in contact with the atmosphere anymore. There's not an easy source of oxygen. There's simply a sink for it. Respiring organisms are consuming it. Okay? And so oxygen disappears from that water. Okay, so that's the simplified story, but there's of course more to it than that. Organisms really need more than just water and CO2 and sunlight to do their photosynthetic activities. If you were to take a plant and you were to put it in a little bottle with some distilled water and CO2 and put it in the sun, the plant wouldn't last very long, okay, because it turns out it needs some more things to work. Most of those things are needed in relatively small quantities. Okay, so when we write a bulk chemical reaction, we don't actually include them because they're fairly minor parts of it. However, they are critical. They have to be there or the reactions won't go. And we call many of these things nutrients. In particular, we call them nutrients if they're things that are relatively rare in seawater in a form that the organisms can use so that they may limit the ability of organisms to do photosynthesis as long as water and sunlight and CO2 are available. Okay? And when we say nutrients, you can think fertilizer because it's a very similar concept. If you go to the hardware store and you buy a bag of fertilizer for your garden, pretty much every bag of fertilizer you buy is going to have 3 numbers on it. In this case, 5, 10, 5. But depending on what kind of, if you're buying grass food because you want to have a nice green lawn, it might say 25, 5, 5 or something like that. Those numbers can vary. Those 3 numbers are the abundance of 3 critical nutrients in that fertilizer. The first number is the abundance of biologically useful nitrogen. Second number is the abundance of biologically useful phosphorus in the form of phosphate. And the final number is the abundance of biologically useful potassium. And it turns out that in seawater, as opposed to a garden on land, 2 of those nutrients are also critical. The first 2, nitrogen and phosphate, in most of the ocean, are the 2 most critical nutrients. Those are the things, if you're up close enough to the surface of the ocean that there's sunlight and there's CO2 and water because you're in the ocean dissolves a fair amount of CO2 from the atmosphere, particularly the shallow parts. What limits the productivity, what limits the biological activity, is frequently the abundance of useful nitrogen and phosphate in that environment. Okay, which is the same thing that's the first 2 things in fertilizer, because it turns out that in most soils, those are also the 2 limiting nutrients. The last one, which is written potash here, but you can think of it as just being potassium, isn't a nutrient in the ocean. Why? Why isn't potassium a limiting nutrient in the ocean? How rare is potassium in seawater? Where is potassium in the periodic table? Does anybody remember? It's right under sodium. Has a chemical similarity to sodium. Sodium is really, really abundant in seawater. It's like 1.5%, something like that. Potassium is pretty common in seawater too. Organisms that do photosynthesis need potassium regardless of where they live, but seawater is chock full of potassium anyway. So no matter how many organisms you have living in a parcel of seawater, they're always going to be able to get enough potassium. It's just pretty common there. So it doesn't function as a nutrient, a limiting nutrient in seawater, just because it's always available in as much abundance as an organism would need. So because potassium is a conservative element in seawater, it doesn't really act as a nutrient. It's always there when an organism needs it, much like the water is. There are some other trace nutrients, iron and silicon, and actually a whole bunch of other things, zinc, so on and so forth, that also need to be present at some level of abundance for organisms to do photosynthesis. And silicon isn't really required for every organism, but it's necessary for organisms that make SiO2 shells like diatoms that want to do photosynthesis. So all of these things that are relatively uncommon in seawater but are required for photosynthetic activity behave in a particular way in seawater generally, which is that in the parts of the ocean where photosynthesis is happening, they tend to get used up and disappear from the dissolved load of seawater. So in the surface ocean, nitrogen and phosphorus tend to be very rare. Organisms that do photosynthesis in the surface ocean, they don't live forever. Eventually they may get eaten or they may simply die and they start to sink. And as they sink, they get consumed, they get decomposed, and that nutrient material tends to get released back into seawater. So once you get below the photosynthetic part of the ocean, below a few hundred meters, actually nutrients start to build up again because there's all this organic material decaying, just like compost, okay, which is a way that we enrich soil by taking leftover organic material and letting it rot a little bit. That makes the nutrients in that material accessible again to plants. The same process happens in the ocean. Once you get below the photosynthetic part of the ocean, any organic material starts to decay and the nutrients in it start to be released. This is going to turn out to be really important because it turns out that any part of the ocean that has deep water that's had been below the surface for a long time, not been photosynthesized in, has usually built up a fair store of nitrogen and phosphorus and other nutrients. If you take some of that water and bring it up near the surface, into the sunlight again, that's going to make it really fertile for biological activity because it already has those nutrients in it. So parts of the ocean where you take deep water that's been in the dark for a long time and bring it up to the surface tend to be the parts of the ocean that are the most productive, that have the most intense biological activity. And by extension, that's where a lot of other things are going to live, like tuna and fish that we want to harvest from the ocean. So it turns out the most productive fisheries tend to be concentrated in parts of the ocean where nutrients are being brought to the surface. So understanding how water flows in the ocean actually ties very closely into understanding why some parts of the ocean are biologically very productive and other parts are much less productive. Where you're bringing deep water up, that tends to be very productive. Okay. So if we look at both oxygen and CO2 as a function of depth, this is the same panel I showed you before. Oxygen tending to be fairly common near the surface and disappearing at depth. Carbon dioxide almost has a mirror image behavior. Near the surface, carbon dioxide, which is here plotted in the form of dissolved inorganic carbon. So that's carbon dioxide and bicarbonate and carbonate and carbonic acid all added together. All the forms of CO2 when it reacts with water. That's what this orange is. And you can see it's almost exactly a mirror image. It like makes a vase or something if you squint at it the right way. Less common near the surface because it's being removed by photosynthesis. More common at depth because it's being regenerated by the decomposition of organic material falling down from above. You'll also notice, by the way, that the pH, the acidity of the water, is also kind of in a mirror image relative to the abundance of dissolved inorganic carbon. So let's look at that in a little more detail. Okay, so let's talk a little bit about acids and bases and how that plays a role in the ocean. So the basic idea here is we're interested in relationships between water and its fragments. In particular, our water occasionally, rarely, will split up to make an H plus cation and an OH anion. This is unusual. About at any given moment in a pot of water that would be sitting here, fresh water at room temperature, about 1 molecule in 10 million would be in a state where it's split up. Okay? So it's pretty uncommon. 1 in 10 to the minus 7. And so in order to describe how much splitting up there's been, we have this concept of pH. And we define the pH as being the abundance of H+, the cation fragment of water, the logarithm of that, base 10, and then we just put a minus in front of it. And so if we go back, and say, okay, 1 in every 10 million water molecules is split up in just pure water at room temperature, that means that the concentration of that fragment is going to be 10 to the minus 7, 1 over 10 to the 7. Okay, so 1 molecule in 10 million is split up, 10 to the minus 7. Let's plug that into this formula. If the abundance of H plus is 10 to the minus 7, the log base 10 of a power of 10 is just the power. So log base 10 of 10 to the minus 7 is minus 7. And then we multiply that by minus 1. We end up with a pH of 7. Okay, if the abundance of H plus is 10 to the minus 7, then the pH is 7. And if there's more H plus than that, for whatever reason, then we can say that it's acidic. Okay, it has an excess of H plus relative to pure neutral water. And if there's less H plus, then the pH is going to be larger because you're taking the negative logarithm of a smaller number. And we can say that the pH is indicating it's basic. It has too little H plus relative to pure water. Okay, so low pH is acidic, meaning there's lots of H plus. High pH is basic, meaning there's very little H plus. And so we can put all kinds of different things on a diagram where we plot how acidic or how basic it is according to pH, with fresh water being right here at 10 to the minus, a pH of 7. Things that we normally think of as acidic, like the sulfuric acid in a battery, would be at very low pHs. Lemon juice, lots of sour things tend to be fairly acidic, as a pH of around 2. Sodas have fairly low pH because first of all, they have phosphoric acid in them commonly, or citric acid or something like that to make them taste tangy, but also, as we'll find out, because they have carbon dioxide dissolved in them. Okay? And then there are some things, particularly cleaning products, tend to be high pH. So bleach and at least old-fashioned soaps tend to have pHs above 10 or so. Seawater, as it turns out, is pretty close to where water is, just pure water. It's a little bit basic. So pure water would be at a pH of 7. Seawater is typically a pH of about 8. Sort of 7.8 to 8.4 or something like that. It's actually, ironically, not ironically, it's very close to blood pH, which is probably not an accident, actually, since our ancestors were all ocean dwellers of one kind or another. Okay, so seawater pH is about 8, slightly basic. And so this comes actually back, it turns out to be dependent to some extent on this idea that CO2 reacts with water to make carbonate. Okay. So just a reminder, CO2 reacts with a water molecule to make carbonic acid, which can then dissociate to make bicarbonate, and that's where most of the CO2 in seawater sits. So what's going to happen if most carbon dioxide dissolved in seawater is like this? If we do something like add more CO2. If we add CO2 to water and most of that CO2 dissolves to make carbonic acid and most of that carbonic acid dissociates to make bicarbonate, what are we generating in the process of dissolving that CO2? Are we making H plus or are we consuming it? We're making more. So what's going to happen to the pH? It's going to go down. When you add CO2 to seawater, it becomes more acidic. CO2 acts like a weak acid when it dissolves in water. So most rainwater actually is slightly acidic. Even if it's clean air, rainwater will have a pH of order 6 or something like that. And that's because CO2 dissolves in the rain droplet and goes through this process of making bicarbonate, releasing a little bit of H+. Of course, if you were in an area that's downwind from a bunch of coal-burning plants and they aren't scrubbing the sulfate and other things out of the air, it'll be even more acidic than that. But even pure, clean rainwater has a slightly acidic pH because of CO2 dissolved in it. All right. What's going to happen if we throw something that is a base into seawater? Something that consumes H+ when it dissolves in water. That will tend to raise the pH. However, because so much carbon dioxide is in this form, in addition to some of the base going to consume H plus or generate OH minus and thus raising the pH, to a certain extent what's going to happen when you do that is that some of the bicarbonate is also going to react in such a way that it actually generates more H plus. Okay? If you raise the pH by lowering the abundance of H plus, bicarbonate is going to tend to break up. And it's going to tend to make more H plus. This is actually the way chemical equilibria typically work. If you have a reaction and something is generated on one side of the reaction, and you remove that stuff from the solution, the reaction is going to tend to move in such a way to generate more of that stuff. Okay, the basic principle is that the system will sort of move to create more of anything that's being removed from the system. So if you do something to seawater, adding sodium hydroxide or ammonia to it would be an extreme example, something that really raises the pH. One thing that seawater is going to do in response is take some of its bicarbonate and react it to make carbonate, thus generating an extra H plus, which will, to some extent, neutralize the base you've added. The fact that most carbon dioxide dissolved in seawater is in the form of bicarbonate, and bicarbonate can actually go either way. It can give off another H plus and become carbonate, or it can suck up an H plus and become CO2 and carbonic acid, means that it acts like a buffer in seawater. If you try to change the pH of seawater, it's tough, because in addition to changing the pH, whatever base or acid you add to seawater is also going to tend to react with the bicarbonate in such a way that the effect on pH is minimized. So seawater is actually buffered. Its pH is buffered to some extent by the fact that there's this stuff dissolved in it that can act either as an acid or a base, depending on how conditions change. Okay, so seawater has a pH of about 8, and it doesn't change very easily. But one thing that does change it is the abundance of CO2. Parts of the ocean that have lots of CO2 in them tend to have lower pH. Parts of the ocean that have CO2 removed from it tend to have higher pH. Right? So this stuff turns out to be really important for understanding why the ocean, for instance, in the deep parts, doesn't like to accumulate calcium carbonate sediments. Okay? It's because in the deep ocean there's lots of carbon dioxide. That carbon dioxide makes the ocean more acidic, and the acid is capable of dissolving calcium carbonate. Temperature plays a role too, but acidity is very important. Okay? So CO2 dissolving from the atmosphere into the ocean and being produced by respiration is actually important for understanding the biological cycle and the sediment cycle of the ocean. In deep ocean, these are usually waters that were last near the surface of the poles. They are very cold, so there was lots of CO2 dissolved in them just from the beginning, because gas is more soluble in cold water. And of course, if they've been in the dark for a long time, they've accumulated more CO2 by respiration and become even more acidic, and therefore are able to dissolve calcium carbonate. All right, so I showed you, let's see, on Wednesday, I showed you this picture of the abundance of freon, of CFC11 in seawater. You guys remember that? Where was it really abundant in the ocean? It was really abundant near the poles, and in particular near which pole? Near the North Pole. In what part of the ocean? Not everywhere. Which ocean was it most abundant in? It was most abundant in the North Atlantic, kind of off the coast of Labrador, Newfoundland and stuff. Okay, and that's, in the case of freon, chlorofluorocarbons, stuff that gets in from the surface, because we, of course, humans have released it into the atmosphere, and it's only there because we released it into the atmosphere. It doesn't really occur naturally in any significant abundance. So the fact that it's in the North Atlantic and in the Southern Ocean, that stuff has gone from the surface all the way into the deep water over the past 30 or 40 years or so, since we've been making it in large quantities, tells us what about how long that water has been beneath the surface? If we have deep water that has lots of freon in it, what can we say about how long it's been since it was last near the surface? Can't have been very long, right? If it was last near the surface 300 years ago, there wasn't any Freon in the atmosphere 300 years ago. We hadn't figured out how to make it yet. So it couldn't have dissolved any. However, if it was last near the surface 10 years ago, the atmosphere was full of Freon, okay, relatively speaking. And therefore, there would be lots of it available to dissolve in that surface water. And if it then sank into the deep part of the ocean, it would bring that Freon with it. So the fact that the North Atlantic has lots of Freon, even in the deep water, means that that water was last near the surface sometime in the last 40 or 50 years. The fact that most of the ocean isn't like that means that it was not near the surface in the last 40 or 50 years. So which part of the ocean would you expect to have lots of CO2 dissolved in it? The part that's been in the dark for hundreds of years, or the part that's only been in the dark for 10 years or so? If CO2 is being generated by the decomposition of organic material, once you get out of the photosynthetic part of the ocean, would you expect North Atlantic deep water to have lots of CO2 dissolved in it? Would you expect North Pacific water to have lots of CO2 dissolved in it? Which would you expect to have more CO2 dissolved? The Pacific. Because that water has been in the deep for a long time, more than 50 years, actually hundreds of years in most cases. So it's had all this time when it's sitting there in the dark, organic material is being decomposed in it, generating CO2, so the CO2 abundance just builds up and builds up and builds up. So the North Pacific is full of CO2. North Atlantic has a significant amount of CO2 in it, but not nearly as much. So which ocean is going to be more acidic? The Pacific. So which ocean is going to be more likely to dissolve calcium carbonate? The Pacific. So which ocean is going to have the shallower CCD? Pacific. Right? Because you don't have to go very far down in the Pacific before you start dissolving all that calcium carbonate. Okay, so the Pacific is more acidic because it has more CO2 dissolved in it, which makes it lower in pH. And it has more CO2 dissolved in it because it's older. It's been in the dark for a really long time. North Atlantic deep water hasn't been in the dark very long. There hasn't been very much buildup of dissolved CO2. Okay? All right. Any questions about pH? Yeah. Acids dissolve carbonates. And let's see, you just finished lab 4, right? So did you all see like the way that you test for calcareous ooze instead of siliceous ooze is by dropping some acid on it? And what did that calcareous ooze do? It fizzes, right? And that's because it's reacting with the acid. It's actually dissolving in the acid. Now, in that case, you're not using carbonic acid. You're using HCl, which is much stronger. But the same basic principle applies. What would you expect to happen to the pH of the oceans if the abundance of CO2 in the atmosphere goes up? It's going to become lower. It's going to become more acidic because CO2 makes an acid when it dissolves in water. So what would you expect to happen if we're pumping CO2 into the atmosphere to the sort of survivability of calcium carbonate in seawater? Is it going to be more or less likely to dissolve? It's going to be more likely to dissolve. And this is actually one of the issues of CO2 that people worry about, aside from global warming, is this idea if we put enough CO2 into the atmosphere and it starts to dissolve in the ocean, it becomes more difficult for organisms that make calcium carbonate skeletons to not have their skeletons dissolve out from under them because the pH of the water is getting lower and lower. All right. Last chance for questions about pH and seawater chemistry. All right. So to finish up, I'll give you the first few slides of a discussion about wind. This is a picture of the North Pacific during a storm, I presume. I hope it's not usually like this. Doesn't sound like a boat that's much fun to be on. And this is what's called a wind sea. So this is a picture of wind, which you can't see very well, very visibly interacting with the surface of the ocean, which you can see well here. in this case generating large waves, but it also does other things. It actually pulls the water around over large distances, as well as making the surface crenulated. So why do we care about the atmosphere in an oceanography class after all? It's because the atmosphere and the ocean actually interact with each other. So in order to understand one, we have to understand something about the other. In particular, we've already learned a little bit how air blowing across the surface of the ocean, because water has such a high heat capacity, can moderate the climate. It can keep air temperatures from varying by much because they can absorb or deliver extra heat to the surface ocean without changing the temperature of the surface ocean very much. Okay? So in the case of LA, our very nice climate has a lot to do with the fact that the atmosphere is interacting with the ocean and exchanging heat with it. That's why our weather doesn't change very much from winter to summer, and it's nice and cool most of the time. I want to draw a distinction between weather, which is sort of day-to-day variation. Is it raining today? Okay, is it a hot day? And climate, which is kind of a long-term integrated average weather. Okay, how much does it rain in the average year? What is the average temperature in January? Those are climate questions. What's the weather going to be like tomorrow? Is it going to rain? Is it going to be windy? Is it going to be a Santa Ana day? That's kind of a weather question. Okay, and there's a time scale difference. Weather is sort of day-to-day, hour-to-hour. Climate is averaged over long periods of time in one way or another. And it turns out that in particular, climate, we're going to kind of focus on, in particular, the direction of wind blowing across the surface of the ocean, average direction of winds blowing across the surface of the ocean, is really systematic on our planet for reasons I'll describe over the next couple of lectures. And it turns out to be very important for driving surface currents in the ocean. Okay, so the wind blows across the surface of the ocean, and in addition to making big waves, it actually drags the surface of the ocean along with it, with some complications because we're on a planet that's spinning, causes surface currents in the ocean. Okay, so what is the atmosphere? We've already talked about this a little bit. It's dominated by nitrogen and oxygen. There's another percent or so of a gas called argon, which is a noble gas. Those numbers are under the assumption that we're talking about dry air, but it turns out that the atmosphere is variable, and its primary source of variability in its chemical composition is water in vapor form. The atmosphere is generally not completely dry, although if you go up high enough, it becomes pretty rare to see water. But at ground level, typically about 1% water vapor in the atmosphere. So after nitrogen and oxygen and argon, actually water vapor in LA is the third or fourth most common gas phase molecule in the atmosphere. It doesn't spend a lot of time in the atmosphere. It's not conservative. It doesn't have a long chemical residence time in the atmosphere, typically on the order of a week. Okay, and this kind of makes sense, right? You evaporate some water off of the ocean, and then eventually it goes up into a cloud and forms rain, and the rain falls back out into the ocean. The atmosphere moves pretty fast, and so that process, on average, only takes a few days. Compare that to the residence time of water as a liquid in the ocean itself. The ocean is much bigger, okay? And so the same amount of water being evaporated and raining out takes a much longer time to replace all the liquid water in the ocean, of order a few thousand years. Okay. One very important thing that's going to hopefully be key to understanding the next lecture or two is the idea that warm air can hold much more water vapor than cold air. As you increase the temperature of the air, its ability to mix up with lots of water vapor increases really quickly. And that's what this figure is showing. On the x-axis is temperature in degrees Celsius. On the y-axis is the maximum amount of water vapor that can be held by the air. And at 0 degrees, at freezing, it's a fraction of a percent. By the time you get up to about 10 degrees, air can hold about 1% water vapor. 20 degrees, it's close to 2%. And if you're in a really hot summer day, muggy summer day, it can be 3% or more. So it turns out that this is really important because if you have air and you change its temperature, you might affect its ability to hold on to water vapor, and you may have air that finds it can't actually hold on to all the water vapor that's in it because its temperature is dropping. When that happens, that's when water vapor forms a liquid, condenses to make clouds. And so precipitation commonly occurs in those places where you have air that's fairly warm with lots of water vapor in it that's cooling down for one reason or another and is no longer able to hold on to all that water vapor. This causes some confusion in this class because I've just told you over the last lecture or two that cold water can dissolve more gas, right? But warm air can hold more water vapor, right? Okay, think of it this way. If it's cold, things like to be in the liquid. If it's warm, things like to be in the vapor, okay? So if it's cold, even gases like CO2 like to dissolve into the water. If it's warm, even the water likes to go up into the atmosphere. Okay, so warm likes gas, cold likes things to be in the liquid, whatever it is. Okay? Now this turns out to be important for one particular reason. One funny thing about our atmosphere relative to just about everything I've talked about, every material thing I've talked about in this class. And that is that air is not very dense, and its density varies a lot depending on where you are in the atmosphere. This is a plot that shows the pressure, which you can think of as being directly analogous to the density. Pressure and density are linearly related, more or less, as a function of altitude from the ground surface up to the top of the atmosphere at 100 kilometers. Okay? What you can see is, at ground level, we have about, these units are kind of funny, they're millibars, which is about 1,000th of an atmosphere. So we have 1,000 thousandths of an atmosphere. So we have an atmosphere. The definition of atmospheric pressure, 1 atmosphere, is what the pressure of the atmosphere is at ground level, more or less. But that pressure falls off very quickly. The density of air falls off very quickly as you go up. Okay? Which is why your ears pop when you go on a plane or you drive a car up to a mountain pass. The air around you is getting less and less dense. The air in your ears is trying to expand, and so it starts to pop, okay, to try to equalize that pressure. So by the time you get to just 10 kilometers high in the atmospheric pressure is a fraction of what it is at the ground level, a third or something like that. Okay? So air expands a lot when you go up in the atmosphere. It's easily compressible. Water is not very compressible. If you squeeze water with an atmosphere of extra pressure, it barely changes its density at all. Rocks really don't like to change their density when you apply pressure to them. If you squeeze really hard, they'll compress a little bit. But neither of those substances behaves at all like air does. Okay? You put 1 extra atmosphere of pressure on air and you have its volume. And you put an extra atmosphere of pressure on a liter of water, and you maybe reduce its volume by, a fraction of 1,000th or something like that. So this turns out to be really important because it means that when air moves vertically in the atmosphere, it also expands and contracts. Okay? In particular, air moving up is also air that's expanding. And that turns out to be important because when air expands, really when anything expands, it tends to drop its temperature. Okay? If you take something that's compressed and you increase its volume, its temperature drops. And this is critical because I just told you that cold air can't hold on to water vapor as well as warm air can. So if you take air near the surface and you raise it in the atmosphere, it's going to expand, its temperature is going to drop, and its ability to hold on to that water vapor is going to disappear. All right, so when we come back on Wednesday, I'll give you some demonstrations of that process of air expanding and losing its ability to keep water vapor.